My name is Sumedh. I'm a senior machine learning engineer. I hail from Dallas, Texas. I've been working in the computer vision space for the last 6.5 years. First, I worked in the healthcare space, and now I work primarily in the retail space. I started working with deep learning back in 2016. Started using TensorFlow like when it was just too new. So as a developer, what we generally do is whenever we have issues, we try to debug and understand what's going on. I'm not the kind of a guy who use like console print statements to debug, but use programming tool like PyCharm, put breakpoints, and try to go like step by step and understand what's going on, where there's an issue, right? Can we do something similar to deep neural networks? That's where I started working towards and trying to see that can we not see this as a black box, and is there a better way to do it? Of course, scientists like Jeff Hinton, Jan LeCun, these guys, they clearly know what's happening in each individual network. When they came up with techniques like dropout, they're like, okay, there's something like bagging. I think to get at that granular level, you gotta like master it. But are there other ways to also do it? So this is when my journey towards model interpretability for CV models started. So today I would like to talk a little bit about how we can interpret deep learning models and how we can get insights from it. How many of you are familiar with deep learning here? Okay. Those who are not, what is deep learning is it specifically for computer vision, ability for machines to automatically learn to extract meaningful features from raw image data. Like to get into the more detailed part of it, meaningful features meaning what is unique about an image, right? Say if you take an image of a dog, you know that the way the dog's eyes, ears, nose is, it's completely different to any other animal in the world. Kind of that's how humans see it. And we are trying to see whether machine can do the same and generalize it, right? So this is what is deep learning. But also the other thing is, prior to deep learning, you had like traditional image processing techniques. Take for example, canny edge filter. It's a very simple edge detection filter. There's a simple algorithm that you run, and then it just gives you the edges, right? But in deep learning, you're not putting any algorithms there, but you're making the machine learn these by just feeding tons and tons of data. So this is what is basically features for a single image, right? Now, what is model interpretability? Let's take a simple example, a simple neural network called convolutional neural network. The assumption here is the neural network is already trained on few animals, in that zebra is one of them, as seen here. And then at test time or inference time, you give an image of a zebra that was not given in the training, and then you feed it through the neural network, and it gives you a confidence. Like it gave you a confidence of 0.7, right? How do you interpret this? Like, okay, you got a 0.7 accuracy, but what is it that the machine actually learned? Like, how could it say it, right? So this is basically model interpretability. How do you interpret your results? So I'll be talking more about that. And the next thing is why model interpretability? A, it is explaining to business and stakeholders, and B, it is to debug your neural network, right? So when I say explain to business stakeholder, a lot of business leaders, they don't know what a neural network is, and they don't want to know as well, right? But when you build something like a simple stop sign detector, which solves a huge problem to one of the CFOs, right? When you go to him, he'll be like, hey, what are you doing? Like, can you tell me more about this? I can't believe this, right? How do you make sure these business leaders understand in a very simple way and not get into the technical details, right? Visualization is too powerful. So can you basically visualize it and say that, hey, I think this is the reason why I'm getting this result, and this is why I feel it works, and I think this is the reason why you should probably invest more or give more attention to something like this. So how do you make it easy for them? And second is debugging neural networks, like how I started about development by using breakpoints. Can you do something similar on neural networks? So this is one of the example. How do you explain CV to business? I took a very simple example of a cup, and the cup is being already trained on, and now a business leader can clearly understand what's really happening. If you just tell him that, hey, this is a neural network, a ResNet backbone, a VGG, which has like 150 layers, he'll not understand. He'll just not understand. How do you actually break it down so that he understands? This is one of the where you can directly tell that, hey, look, the initial layers, it's actually learning the outer side. Then when you go deeper down, it's learning the edges. Then when you go more deeper, it's trying to learn the individual features of a cup, which is completely distinct from any other. And then this is how I'm finally giving the answer, right? So this way, if you can clearly showcase the value that a deep learning project can bring to the table to business, that's where I think you have more success and more attention to the project that you work on. Second thing is debugging neural networks. How many of you have actually trained a deep neural network? Okay. So when you train a neural network, the happy path is basically your loss function has to reduce, right? If your loss function doesn't reduce, then that's one of the indication that the neural network is not learning. For those who don't know what's really happening here is, you're trying to evaluate how well the model is learning on the data that you provide, and that inference time when the model is already trained on, how the performance is like. In this case, clearly it's overfitting. And there are situations wherein on a happy path, the train and the validation, they kind of go together. This is when the neural network is learning really well. But this is not the only way. Of late, what's happening is with the crazy progress in deep neural networks and the research that's going on, any off-the-shelf model you take, and when you run your custom data, definitely your custom data is not that big. It'll always converge. So this term is basically called converging. It'll always converge, but can you go deeper? So I can share one example that I actually faced at work. So we were actually training somewhat like a one-shot based neural network. When we were actually training a one-shot based neural network, the loss function started going into like negative, right? When it started going into negative, like it started with positive, started going towards negative, and then there was a small error that I had to fix. That's how I got to know. And then the loss function started like, it didn't go to like 0, but it was like 0.008, 0.00834, 835. It was like not going towards 0, but it was like so low. But the performance at inference was really bad. Okay, how do we figure out what's really happening, right? Apart from this one signal of just noticing from the training and validation logs. Certain ways I figured it out, and I would like to share that today, apart from the general train and validation laws that you go through. Ways of debugging neural networks. There are newer techniques under the umbrella called explainable AI frameworks. It's called XAI. You can find a lot of tools there. There are some visualization tools that you can use, and there is some heuristic-based understanding that you can do. Any one of you know about any of the three? Okay. Like, can you tell what you know, if possible?
Yeah, I use visualization tools. I use visualization tools like plotting or.
Got it. Okay, sounds good. Got it. So for those who don't know visualization tools, these are basically tell you how your data is going to be in like 2 dimensions, because you cannot go beyond 2 dimensions. It's really hard, maybe 3, but not beyond that. but how to make sure that a human himself can understand, right? These neural networks, the dimensions are huge. It goes into like thousands or maybe hundreds, and your brain, unfortunately, they don't have that capacity to imagine that way, right? So how do you do this? Explainable frameworks, I can start with that. One is called as SHAP, the other one is LIME, and the third one is gradient-based visualization. So the first is called Shapley additive explanations. Here you can see an example of an American egret, right? And then you have an example of a speedboat. Now you can clearly see that the model is focusing on the neck part of the American egret. And similarly for a speedboat, it's clearly at the point where you have the speedboat. That means the model is trained really well, right? So these are some intuitive ways wherein you can actually identify. To get a little deeper into this, what it does, SHAP framework, it takes inputs from all the layers of the neural network, all the variables from the neural network, and it tries to give you a summary of how the entire neural network is performing. This is what SHAP does. It's not on an individual layer level, but it takes the entire neural network, sums it, and then gives you a snapshot of how the performance is by just feeding an image, right? What you can do, a couple of things is, sometimes you might have a bigger image and you might have an assumption that if I give a bigger image with more noise meaning more background, it will work. Sometimes it works, sometimes it doesn't work. But in situations like these, you can clearly know that you may have to crop the exact region that distinguishes from all the other classes, right? Now the second one is called LIME. LIME is local interpretable model agnostic explanations, right? So what LIME does is, it takes the original image. What it does is, it does a superpixel segmentation. That's a traditional image processing technique. What that does is, I don't have that slide, unfortunately, I'm sorry about that. What it does is, it groups all the colors together and it creates clusters. So once you have these clusters, these individual clusters are fed through like a logistic regression model, and each individual cluster is, you can take it like a patch, right? All the reds are together, all the greens are together, all the backgrounds are together, right? You take the entire patch and you feed it to the logistic regression model, and then you get an output from that. Based on that, you'll know where the emphasis is. This is the other way to know, right? In this, you can know, okay, where the emphasis is. One is in the SHAP technique, the other one is with LIME. So it's a trade-off. It depends based on your use case, whether you want to use SHAP or whether you want to go with LIME, right? The next is the gradient-based learning. Here, the model is clearly trained on a car, and then using a heat map, you'll know which part of the car is the model actually focusing on, right? So in this, there are certain other techniques, but this is a slightly laborious process. What happens is, you take the output of every layer of the neural network, and then you deconvolve back to your original image to understand what's happening. So you can literally visualize every single layer, and then you'll clearly know what the neural network is learning. There's a paper by this person named Jason Yosinski on visualizing neural networks. He actually visualized facial images by just running through the network, and surprisingly, the neural network went to an extent of identifying individual eye. Right? So that way, if you visualize, it's super helpful. For example, one experience from my work, we were actually detecting these fire extinguishers and parking signs, exit boards, the images that we were getting, it had like a spotlight like this. And the neural network was actually getting confused. When we actually visualize certain layers, I know it's a totally laborious process, sometimes may help, it may not help. We actually saw that the network was also learning the lights. And then you had to figure out a way to cut those down and then clean your data. But in this way, what you're doing is when you're actually cleaning your data, you're more methodical and you're like going with the proper reason rather than just taking a shot and trying out, right? Just hitting every layer, but you're just being more methodical and more clear and nuanced in your approach. This is gradient based. The next is visualization tools, right? Sometimes there are situations where you have to train a neural network, sometimes you don't have to train a neural network. But how do you know the performance of the neural network, right? So what you can do is you can cut off the final layer, which actually gives you the class name, and you can just take those embeddings and then you can either do like a PCA or a TESNI. What it does is it breaks down a high dimension to a lower dimension, keeping only the most useful information, right? And that way you can cluster it out. The other way, it is slightly compute heavy. What you can do is you can iterate, and after each iteration, you can take a snapshot and try to understand whether the embeddings are being pushed away or not. If the embeddings are not getting pushed away, that means the network is not actually learning. Such techniques you have to use when your loss function starts at a really low value and it just keeps going lower and lower, to a point where you clearly don't know what's happening. Should I just increase the epochs to like 300 or just keep it at 50? What should I do, right? In these situations, you can clearly know whether the clusters are coming or not, or like you get insights that way. And this is something that was super helpful as well. But it's computationally heavy because once you do finish your training, you need to write your custom code to generate this with your test data set, see what's happening, use certain metrics for the cluster distances, and then go back. This is something that's not available in like traditional open source frameworks like Keras or TensorFlow. You may have to write it by yourself. This is what I was talking about, how you can interpret models with visualization tools. The next is heuristic-based learning, right? How many of you have trained an object detection model? Okay. For those who don't know an object detection model, you take, like say, an image has a car, and in the background it has, like say, trees. But when you pass the image of a car through the model actually gives you a bounding box of where the car is, right? Now, I'm pretty sure the strategy is not to train from scratch, but you'll just take an off-the-shelf model and then do some kind of transfer learning on your custom data. Say you want to detect something extremely specific, right? You want to detect, like say, patches on the road. And of course, with an off-the-shelf model, you can't do it, right? How do you check whether the model is learning those patches? That's when you can start training initially. Oh, I don't have an image for that. I'm sorry. I actually had an image for this. I think it's missing. So basically, it had an image of a person sitting in a car. It was about only training images to detect people sitting in a car, just people sitting in a car, not pedestrian, right? In these situations, how do you check whether your model is learning? You can take a small sample. First, you can train it for certain epochs, then take a small sample and forcibly give the model these images wherein there is a person sitting in a car, and then see whether it's able to segment or it's able to give the bounding box. If it's giving the bounding box, then I think the model is learning these newer features, like the way they're sitting, the posture, and things like that. So this is what I call as heuristic-based learning. Just take a sample, try it out, see what's going on, and then take it forward. Then how do you take this and then have your KPIs or go to your business, right? In the industry, the data sets keep changing, the standards keep changing, but on a business level, all they care is metrics, right? Now, if you say my model is giving 99%, the business is like super happy. But internally, sometimes what data you use changes, right? If the data is not challenging enough, then if you get 99, then it's not really great, but for the business, it's okay. But internally, if you have, like, say, some blurry images, keep some tough images, and your metrics go low, that's still fine. That's not too bad. And also, after you hit a certain point where you have trained your model enough, each person that you go up is itself a Herculean task. And it's like something that you really have to appreciate yourself and pat on your back, because it's hard. Every percent increase that you go, it's something new that you have to learn. And that's the reason these metrics have to be like very well defined, and it's not always 99 means the model is doing really great, right? It depends on the data set and how the business understands. Also, like if it's on the research level, what kind of metrics you keep, and then decide on how you can take it forward. Applications. So this really happened with me in the healthcare space. So I actually worked on detection of endoscopic images, cervical cancer images, oral cancer images, and skin cancer images as well. Okay, you have a great model, it's working very well. If a person has an abnormality, how do you make sure you are right? Or how do you even tell the doctor that the model is correct? The model says, no, it's not cancerous, but the doctor is like, no, it's cancerous, right? How do you explain these things to the doctor very quickly? Like, it should be super quick. These situations, these model interpretability techniques help. You can clearly say that, hey, this is the heat map I see. This is where I think I could see an abnormality, because in the end, it's a pattern recognition, right? It's a pattern recognition problem. So you can clearly have a small tool which can show that, hey, I think the model is giving this, but it's giving this because of these reasons, right? So that he understands what's going on and doesn't take it on an ego level that, like, how can a model just say something that I've been practicing for the last 20 years. So, yeah. And the second thing is training neural networks. Like I was explaining about how you debug. When you debug is when you actually learn how to train your neural networks better. And these techniques actually help in that. So, yes, any questions for me?
Thank you so much for the talk. This is fascinating. I'm wondering if you've ever used any interactivity in some of the visualizations that you've used for interpretability.
Any interactive what, sorry?
Interactive visualizations.
Yes, I did. There is an open source tool called Keras Viz. I had used that. Again, that's where it gets super laborious. It's like they just give you a bunch of images of different layers. You have to go through each to understand what's really happening and try out few images, not a lot, to really see what's happening. Like an example I gave, when the light was on the part that was interesting to me, the model started using that as a signal and started highlighting that in its activation function. So that's when I realized I think I should cut it down. So, but the problem is the versions are changing. I think now there could be better tools, and that may not work. This was like 3-4 years ago. Yeah.
Hi. You mentioned SAP and Lime,
Yeah.
and you also said that it's a model agnostic. What does it mean, model agnostic? So it doesn't depend on the model?
Yes, it doesn't depend on the model.
It does depend on the accuracy of the model?
Not even the accuracy of the model. It creates, I mean, it just sees the performance of the model. Of course, you need a model, and then it feeds the data in a certain way to the model, sees the output of that, and they have some equations that they run, and then they spit out.
And do you have any recommendation where I should use SAP, or where I should use Lime, or anything I can use?
That's a trade-off. So this is something that even I've been trying out. Both are useful sometimes, so it's good to try out both, and then if both give you the same result, so it kind of helps you that way. Yeah.
Thanks for your talk. The field of expandable AI has also a lot of I would say dissonant voices that shows that those visualization techniques can actually be misleading. There's quite a huge body of research that shows that often, especially gradient-based visualization methods, are unreliable, or they highlight things
Right.
that you can demonstrate in the end actually do not matter. And so knowing about the existence of that, how do you decide if you can actually trust the explanations from these visualizations, especially when you go back to your business leaders? It's like, you know, sometimes it's very suggestive, like you showed, it clearly focuses on the object.
Right.
But there's a lot of research that shows that even if it focuses on the object, it actually might be misleading, and it's not as straightforward as it seems to be. So how do you decide, you know, do you keep up with the literature to make sure that some of those visualization techniques are actually consistent, or usually you have to do, say, 100 different examples and see if the explanation is indeed consistently related to the result? So
Right. I think like one of the example, we had to identify a specific pattern. Of course, not like an Aruko marker, but a specific pattern in a particular item. So what really happened was the model would not give the right result, right? If the model gives the right result, it's like great, you will not even take this path, right? So since the model didn't give it, that's when I had to take this part to understand like what is it that it's actually understanding. So it was like some kind of a pattern that we had to identify, and it had like a yellow background. So it started highlighting the yellow background more using just simple GradCam visualization. It started highlighting yellow more and started focusing less on the pattern. And that's when our research moved a little towards how we can focus more on the pattern. And we try to do like one-shot learning based with giving more like negative images for a specific and a positive image for a specific, and then trying to focus the model more towards the pattern and not the background. So it kind of gives you these insights to try out, and if that works, great. In our case it worked, but sometimes it doesn't work too. So that's how it just opens you up to see how you can solve the problem. Right.
Few more minutes for questions, so take your time.
You mentioned that you've been using Lime and SHAP, and so could you talk about the cost considerations or the time that it takes for Lime or SHAP to generate explanations, and how what you've encountered with respect to that? And also, could you also mention something about the stability of the explanations generated using the gradient-based methods? Have the explanations been stable across similar inputs? And have there been occasions where they haven't been stable?
Okay, so Lime and SHAP, actually they are more cleaner frameworks compared to the earlier ones, the gradient based that came out, and then subsequently when Lime and SHAP happened, they're more cleaner and nicer, easy to install, easy to run and check. It's not too bad. Gradient based, the problem is there were so many gradient based techniques that came out, And so this visualization part is something that was helpful to me, trying to go through the layers and see that. Lime and SHAP was more recent. Back then it was just GradCam visualization. So I just had to rely on that. But off late, like after this, I haven't really gone back to that and made a comparison. I still strongly feel Lime and SHAP are way better compared to that. Yeah.
Thank you for the talk. So since you have some extensive experience with medical image analysis too, as you mentioned, I was wondering that, like specifically when we are trying to convince the clinicians,
Right.
the problem is that like if a particular exam is like, let's say positive, like it has cancer image, let's say.
Right.
So, so all these heat maps based techniques can, help us localize the tumor, let's say. But specifically for negative exams, it is not trying to localize anything. The heat maps kind of identify the portions with high intensity that it used to say that this particular exam does not have cancer. But that may not be a sufficient evidence to kind of convince the clinicians to adopt this particular model into their clinical settings. So do you foresee the development of these explainable AI techniques, maybe specifically in the healthcare industry, to kind of have some more detailed explanations accompanying just these heat maps?
Yes. Since I've worked in the retail and a little bit on the insurance and healthcare, healthcare is like extremely sensitive. When you give a certain result, it's too emotional as well. When you talk to patients or when a doctor says, right, you got to be like 100% sure or maybe even higher. When it comes to these other areas, you can use other signals, right? Let's say in autonomous vehicles, what they do is they have multiple signals coming. Like say if you see a person, there'll be like a radar saying the same thing, camera saying the same thing, a point cloud saying the same thing, and you're like sure. But in healthcare, it's just that one thing, right? And to give you an example, I was working on endoscopic images wherein the torch was actually, it has like an inbuilt torch, and that actually highlights the area so that you can capture better images. Most of the times the network would say it's cancerous, right? So that's when, to make sure you are 100% sure on what you say, it's better to give an explanation. Sometimes you might be wrong, but if you can say to the doctor that, hey, I think we are totally wrong, this is the reason why we are wrong, maybe we need more images of this, but this is literally what the model is telling. And that way you can convince it to him than just saying yes or no, because it can work both ways. A false positive, it's like it's slightly not a good situation to be with. So this is one of the ways that you can try.
Thank you.
Yeah.
So when you're embarking on a training run and you're looking at your learning curve and assessing your loss and figuring out a good place to stop model training, because neural nets are computationally expensive to train, do you have any tools or visualization resources that you would recommend to assess essentially model training against something like GPU cost, especially for business stakeholders who might be wondering about the costs that get incurred during model training?
So, so you're saying that what about the GPU cost and how do you explain the GPU cost during training?
Yeah.
Okay. So you need to show value first, right? And these are certain techniques that you can use to say that, hey, I think I really see a value, but I see a OOM error happening. Sorry, just kidding. I'm seriously seeing an error here because I see that there's so much data available with you all that we can do so much, and you can just start with something small and then totally nail it completely, like as a prototype, and then show it to them. And these techniques, thankfully, will they get convinced, right? And that way you can tell them and be like, okay, I think I may need a higher GPU to give you a better performance with this. It's hard. You can probably go in that route.
Thank you.
Okay, we're going to have to wrap it up in the sake of time, but I want to thank Sumedh for taking the time and energy to prepare this presentation. So thank you very much.
Thank you. Thank you, everyone.